Hi, this is Professor Fernandez, and we are in this video going to work on the beginning Module 1 of Lesson 6. This lesson is about partial derivatives and the chain rule. So there is a lot to cover in this lesson because we are 6 lessons now into the course, and this is really when we start getting into the meat of the course. This is a multivariable calculus course, and thus far in the course we've actually done very little calculus. We've only recently started doing it. We've been spending most of our time just getting acquainted with three-dimensional Euclidean space, with the vectors, the vector viewpoint of space, and we just recently started talking about multivariable functions, limits, and continuity. So this is really the lesson where we start to see where all the magic happens in terms of porting over the calculus results we know, like derivatives, into the multivariable context. This is the lesson preview. Again, I encourage you to read through this. This first module is going to focus on partial derivatives. And there is a real world context here that I put in because, we live in a world of change. And anytime you think change in mathematics, you associate that often with derivatives and calculus. So this particular example application comes from economics. Very, very briefly speaking, if you consider a simplified model of productivity, then the production function could be a function of multiple variables. Here, we're considering labor, capital, and natural resources as the variables. So you might ask lots of interesting questions. You might ask, how does production change as a function of labor? Assuming I don't change the capital or natural resources. Or how does production change as a function of the natural resource availability? Assuming I don't change labor or capital. Those are all questions that turn out to have something to do with what we're going to do in this module, which is the notion of a partial derivative. And then if you want a more in-depth analysis that will tell you if all of these three variables change, how does the production function change? That actually has to do with the second major topic of this lesson, which is the chain rule. This is an example which gets application, I should say, which gets revisited in the practice problems. So I encourage you to read through it and also attempt that practice problem. So let's get right to it. First module about partial derivatives. You no doubt recognize this word from single variable calculus. Why partial? What does partial mean? How can a derivative be partial? We'll get there. The first thing I want to do is give you a nice anchor of an application, or more like a real world context that's going to help you to think about partial derivatives, and then going forward think about just differentiation in the multivariable context. And that's effectively hiking, or just walking around hills or mountains. So I have drawn something that hopefully looks kind of like a small landscape. Maybe you're off in California somewhere, or I don't know, somewhere in the Rocky Mountains, or you're doing some just simple hiking somewhere near where you are. So let's assume that you are standing at the red X. There you are. And the question is, if you want to look around and from the immediate landscape around you, and you start walking around, you are going to be met with differing levels of resistance. So, this is a higher sloped area of the landscape. So to kind of go up that little hill is going to take more work than maybe to go this way, which seems to have a gentler slope. This way kind of seems to be sloping down, so it might not take any work at all, although you might want to be careful not to fall over. The point is that depending on which direction you decide to walk in, the elevation of the landscape changes. And it changes in a different way. So what I want to do now is take this landscape, reproduce it, and then I'm going to put it inside a coordinate system. So I'm going to think of this now sitting inside a coordinate system. So let's put this in R3. There we go. X, Y, and Z. All right, so let's pretend that this red point is standing above the point A comma B in the x-axis, and that this point is now A comma B comma F of A comma B, where this surface, the landscape that you are trying to walk around, is the surface Z equals F of X, Y. The question here now is, how do I use what I know about calculus to describe these changes in elevation as I move around? This can be a complicated question, so we're going to start in a simpler way. We're going to say, okay, if I move parallel to this new x-axis that I've introduced, I haven't really told you how the surface z looks, but maybe it looks somewhat like that. So I'm trying here to draw the curve, maybe make it a little thicker, that is parallel to the x-axis. You could move that way, and that's kind of like this curve then represents the changes in elevation that you would feel. What if I tried to move parallel to the y-axis? So again, I haven't told you much about this function, but it might look something like this, right? And this would be the curve that's parallel to the y-axis. You can see that depending on whether you walk parallel to the x-axis or parallel to the y-axis, you're going to have varying levels of difficulty doing so. And these curves that I've drawn now are curves that are single variable functions. So I can think of this blue curve here as a single variable function, and this is specifically the single variable function where I'm keeping the y value constant because I'm walking parallel to x. So this is f of x comma b. And I'm still going to call that z, but now I'm going to call it z of x because now z has been reduced to a function of x. Right? So along this blue curve, the y value doesn't change, only the x value. And the z value, the elevation, does change. So z is a function of x. Over here, similar thing happening. Here, I'm walking around parallel to the y-axis. So I'm assuming that my x value is the same, which is a. And I'm leaving my y value unchanged. So now this is the curve z of y. So now the main insight that we are coming upon is that I can take this two-variable function, and by walking parallel to the x and y axes, I can make it into a single variable function. And now I can differentiate like I normally would. I could, for example, find over here the derivative of z with respect to x. And I could up here find the derivative of z with respect to y. This brings up our first potential point of confusion. We are used to using prime for derivatives in single variable calculus. There was only one variable. So the prime meant differentiation with respect to that variable. Now things are getting a little confusing. This z's variable is y. This z's variable is x. But I'm using the same prime notation. So we're going to remedy this in a minute. But I want you to keep this basic picture in mind. So what we're trying to do is take a two-variable function, and by momentarily fixing one of the variables, meaning I'm going to make it equal to a constant, I am turning the two-variable function into a single variable function. Then I can apply everything I know from single variable calculus and calculate a derivative. So this leads to this definition, and this is effectively what the route to partial derivatives. So suppose I have a function with domain D. Its partial derivatives are the functions f sub x and f sub y defined by these two. Okay? So let me go through what these are and just relate them for two things that you already know. So let's look at this one really quick. So fx of xy is the limit as h goes to 0 of f of x plus h y minus f of x y over h. A few things you might notice about this definition. Remember that in the single variable case, this was the limit definition of the derivative. There it is. So if you compare these two, what has happened? Well, we're now dealing with a two-variable function, so that's a significant change. But this second variable, actually, we're not changing it. So we're doing exactly, if I scroll up here, what I did over here, right? We're thinking of that second variable as a constant. We're thinking of it as something that is not going to change for the purposes of calculating this limit. Indeed, this is a limit as h goes to 0, and the only place you see h is over here, added to the x. So this is kind of the same difference quotient that you're used to seeing here, right? Except that there, in this case, there is an additional variable y, but we're not changing y. So this is what is meant by a partial derivative up here. So when you hear the word partial derivatives, it's going to be referring to a derivative in the direction of a specific axis, x or y or z, or whatever other independent variables your function has. So similar thing happens with the second partial derivative, f sub y. Notice that a very, very similar thing is going on here. Here, the x values are staying the same. So the partial derivative with respect to y is kind of like what we were doing up here. We leave x unchanged, and we only consider how the function z varies as we change y. Indeed, look at what's happening here in the difference quotient. The only place h shows up is here. So we're comparing the function's value at x and a little bit after y to the function's value at x and y, and then taking the limit as h goes to 0. So that gives us, again, another derivative along the y direction, which is basically the partial derivative f sub y. So we're going to say much more about these partial derivatives in a minute, and we'll do some examples, but let me just finish with some quick information about notation down here. So the notation that I've just given you, this subscript notation, this is pretty standard notation, and it's pretty compact. It's pretty nice. There's also two other notations that you might see pop up. This is the first one. You, in Leibniz notation, might remember this standing for the derivative, f prime of x, when the function is y equals f of x. So this was our Leibniz notation. For partial derivatives, we have this similar notation. This funny symbol here is kind of like meant to be kind of like a d to remind you that we're talking about derivatives, but it's not an actual d because this symbol means something different in the context of multivariable functions. We'll get there. It has to do with the chain rule. But for now, just remember that this kind of looks like a d. It's meant to look like a d, but it's not exactly a d because it's not the same type of derivative that this is. It is a partial derivative. So this is the second notation for partial derivatives. And then the third notation is, brings back the d. In this case, capitalizes it, so d sub 1. 1 here refers to the first independent variable x. D sub 2 refers to the second independent variable y. Okay, so these are the two notations, and just like when you read this in calculus, you would say dy by dx or dy dx. You could read this as del f del x, or you might just say partial f partial x. If you want to do away with all that, you could just say f sub x or fx. So lots of different ways to talk about partial derivatives, to denote partial derivatives. And now we have a little bit of a better sense of what this concept is stemming from here. Okay, I'm going to draw you one more picture, and then I will show you this picture in interactive animated form before we go off and we do our examples. So the picture I'm going to draw you is going to illustrate now partial derivatives in the sense that we understood them, or connected to what we understood about single variable functions derivatives, specifically tangent lines. So I'm going to draw in this picture a surface. So here is my surface. So it's kind of a curvy surface. There we go. And I'm going to draw in the middle, as before, I'm going to draw a point. And this is, oops, that's a big point. This is the point AB, f of AB, as before. So it is the point over the point AB on the xy plane. And then I'm going to draw the curves that are on this surface, as I did before, where I'm keeping x and y fixed. So to do that, I'm going to first duplicate this twice. Let's see if I'll have enough space to do that. All right, I'll do one each. So here what I'm going to do is I'm going to draw the curve that is keeping the let's see, I'll do y first. So let's draw the curve that's keeping the y value fixed and letting the x value vary. So by doing that, I'm effectively going to be drawing, here is y equals b. Oops, I'm trying to use the red color here. Great. So there's y equals b. And this is kind of the line that equals y equals b. And the curve that corresponds to that on the surface would be something like this, right? So all of these points map onto this black curve. Great. So this black curve that you see is the curve. Let me get rid of some of these arrows here. That is the curve. X value changes, y value is b, and the function is x comma b. Okay. So if I now think of, I asked the question, what is fx at a, b? Okay. Well, this black curve here in the figure is the function fx comma b. So if I look at f of x comma b, if I look at f sub x of x comma b, that is going to be just a single variable derivative because this is a single variable function. So this is basically the derivative of this black curve with respect to the direction it's going in x. And therefore this down here is going to be the slope of the line tangent to this curve, the black curve here, the slope of the line tangent to the black curve at x equals a. Okay, so if I draw that, I'm going to draw that slope of the tangent line in green. There it is. So what is fx of AB? The slope of the green line. Okay. So again, if we had to do this reconstruction over here on the left-hand side, what did I do? I drew this curve, which was the curve x varies, y is b, and the function is f of x comma b. And then at the point a, b, f of a, b, I drew the tangent line to this curve. How would I find that tangent line? I would differentiate this function, producing the partial derivative, and then I would substitute in x equals a. So therefore that is what fx of ab means. Okay, I'm going to do this all over again, and I am going to plot the duplicate the same plot to show you the same picture with fy. And then we'll look at how this looks in technology, and then we will do an example. Great, so let's duplicate this. All right, and then I'm going to get rid of the curve here. So I'm going to do the same thing over again, but in terms of y. So in terms of y, what do I do? Well, so if I want to now fix the x value to be a, here's x equals a. So here's the line x equals a, it goes like this. And I look at all those points evaluated on the surface, then I might get a curve that looks like this. Okay, so again, I'm thinking about each one of these points mapping to this curve. Great, so this curve has is a set of points where x is a, y is free, and the function is f of a comma y. So as I look at this curve, if I want to take its derivative, then I will end up producing the derivative in the y direction at point A, that doesn't change, as a function of y. And therefore, if I draw the slope of the tangent line, or if I draw the tangent line at the point AB, it's kind of a horizontal tangent here. So the slope of this line is fy of a comma b. Okay. So these are the pictures that I want you to keep in mind. But in calculating any of these two partial derivatives, what we are doing, mechanically speaking, we'll see this in the examples, is we're just ignoring one of the variables and differentiating in terms of the other. And by ignoring, you could think of it as setting one of the variables, x, let's say, to a constant, and then differentiate in terms of y. That's what we're doing in terms of the mechanics when we do actually calculate partial derivatives. Graphically speaking, we're doing these two things, right? We are pretending that one of the variables is constant, like, for example, x equals a, and that reduces a two-variable function to a single variable function. And then when we calculate slopes of tangent lines, that's exactly what the partial derivatives are, the slopes of those tangent lines. Okay, so let me show you a little bit of this in the technology world, and then we will come back and do some examples. All right, so this is a function that I have put in here, and this function is has lots of hills and valleys, 2 hills and 2 valleys. So it's kind of like the landscape that I was talking about earlier in the video, where you can imagine yourself standing somewhere, maybe at the origin, and you're trying to figure out where to head next, if you're hiking this function. So one thing to notice about this function is that it's flat along the x and y axis. See how it's flat? I'm there looking along the y-axis, and if I look along the x-axis, it's also flat. Why is that? That's because this is the function here. If x equals 0, z equals 0. Doesn't matter what y is. If y equals 0, because of this term, z is also 0. Doesn't matter what y is. So that explains why the function is flat along the x and y axes. So if you're standing at the origin, right, as you can see here, you aren't, sliding depending on where you came from. If you're standing at the origin, your elevation is 0, is what I want to say. And then you have a choice of where to move. So now let me do one thing. Let me turn on this function and try to give you a better sense of the contrast by changing here the colors. Great. So what have I done? So I turned on this function over here. What is this function? This function is our original function, the surface, where x equals 1, right? So it has 7xy, x is now 1. It had an x squared is 1. And so I'm just going to pan around so you can see. So if you were, if this function represented an actual, set of hills and valleys somewhere near your house, and you went outside and you stood at the origin and you were trying to traverse these hills and valleys, if you walked, 1, foot, mile, whatever the distance is up, and then you wanted to decide to walk just, along what is this fictitious y-axis, this is the curve that you would walk along. Okay, so I'm going to actually turn off here the function so you could see just the curve. See, so that's the curve that you would feel if you were walking just along that x equals 1 slice of the function. So this is a single variable function, right? Look at it. It's z over here. Over here, it's z equals a function of y. So I can take the derivative of this. What would result is effectively z sub y, the partial derivative of z with respect to y. And I can draw tangent lines, and I can look at slopes of tangent lines, right? And I can use single variable calculus. But in doing that, I will have just, if I go back to the main function, what I will be doing is I will be calculating the slopes of tangent lines at a particular, along a particular direction in the function, on basically the function graph cut by the plane x equals 1, right? That's what produces this curve. I'm going to show you another one. So here is another slice. So what am I doing here? Well, on the left-hand side, you can see how I got this, is over here, I set y equal to 1, and I actually did not do that correctly there. So let me fix it. So I'm going to get rid of this y, get rid of this negative, and that will become just 7. And then I'll have to change the y value from 1 to 1.05. Great, so that fixes it. So here we are at y equals 1, and that is the curve that is on the function. And similar thing, if we turn off the function, this is now very clearly, it was even before when the function was turned on, a curve, a single variable curve. If we were to find the derivative along, of this function, which is purely a function of x, we would be finding z sub x, the partial derivative of z with respect to x. And what would that tell me? That would tell me how the function z changes with respect to only x at y equals 1, right? Because y equals 1 is constant for this function. There is no y. Okay, so this has been just a very quick introduction to partial derivatives from the graphical side. And now that we know what we're talking about, let's go back to the examples and let's actually calculate some partial derivatives. Okay, so example 6.1, let f of xy equal this, and let's find, first of all, fx of xy. So like we mentioned before, to do that, the mechanics of calculating a partial derivative, because we're calculating the partial with respect to x, every single term involving a y, we think of, I should say every single instance of y, we think of as constant. So you might as well think of this as x cubed plus x squared times, I don't know, 2 cubed, plus x over 1 plus 2 squared, minus cosine of 2. It really is intended to be, thought y is really is intended to be thought of as constant. I actually do not recommend, doing this in this way. I recommend thinking of it in this way, but not doing this in this way, because, when we differentiate this with respect to x, we're going to get a 2x. And if you're really using numbers, you might be tempted to combine these numbers. And you might say, oh, this is 2 to the third 8 times 2, 16. There's a 16x term. But actually, there won't be a 16x term. The term you end up with should have y's in it. It's just that when you differentiated it, it should, the y's should have acted like constants. So let me illustrate for you then what we actually get when we calculate this partial derivative. So we are differentiating with respect to x. So the first term is a term with respect to x, so the derivative of that is, as usual, 3x squared. Now for the second term. Because we're thinking of y as a constant, this is x squared times constant. It will take a while to look at y cubed and think constant, but there is a context that this is happening in, and this is the partial derivative context. So thinking of this as a constant, to differentiate this whole thing, we apply the constant multiple rule, which means we keep the constant and then we just take the derivative of the function and then we multiply back the constant. So that is the partial derivative of that with respect to x. So you can see how the rest of this is going to go. When I look at this term, even though it's x divided by 1 plus y squared, for the purposes of f sub x, y is constant. So this is x times a thing which we're thinking of as constant. So the derivative of this whole thing with respect to x is the derivative of this with respect to x, which is 1, times this constant, which is 1 over 1 plus y squared. And then this one is the easiest one. We're thinking of y as a constant. So cosine of y is also a constant. It's like saying cosine of 2. And the derivative of a constant is 0. So there's nothing left to write for fx. So this is my fx derivative. Again, it will take some time and lots of practice. So I definitely encourage working through the practice problems to do this. Let's look at number 2. So how about df, or del f, del y? This is the partial derivative of f with respect to y now, not x. So now everywhere we see an x, we're going to consider it a constant. So the first term, x cubed, might as well be a constant. So its derivative with respect to y is 0. The second term, now x squared is the constant, and y cubed is the function. So its derivative is the constant times the derivative of y cubed with respect to y. And then second term, third term here, the x over 1 plus y squared, now y is the variable and x is the constant. So now we're thinking of this as 1 plus y squared to the negative 1. And we're thinking of x as constant. So the derivative there is, with respect to y, 1 plus y squared to the negative 2 times 2y. So there I'm using the chain rule from single variable calculus. And then the last term, this is now a function of y, and y is the variable we're differentiating with respect to. So I do take the derivative. And the derivative of cosine of y is negative sine y. With the other negative, turns it into a positive sine y. Okay, great. So that is my derivative. I could simplify it, but I'll just leave it as is. And then last one here, I want to calculate fx of 1, 1. So this means two things. It means, first of all, calculate fx of xy, and then substitute in 1, 1. So to do that, I am going to plug in x equals 1, y equals 1. So I get 3 plus 2 plus 1 half. So I get 5.5. Okay? And the reason I put this as the last part of the example is that I can show you what this looks like graphically. So what I'm going to do now is I'm going to go back to my technology, and I'm going to plot this function for you. It's a little crazy looking, very steep in some places. And then I'm going to show you how to think about this based on everything that we just said. Before I get there, remember that this is the derivative, partial derivative, with respect to x at this point. So this means that if I go to y equals 1 on the function f of xy, and I create this single variable function of x, and then I take its derivative, producing this function, and then I plug in x equals 1, or I look at x equals 1, I will get 5.5. And this will be the slope of the line tangent to this function at x equals 1. And remember, this function is a curve at y equals 1 of f of xy, which is where all this came from. Okay, so if you follow that, great. If not, let's take a look at the technology so we can see this in action. So I'm going to turn off these two functions here on the left, and I'm going to turn on my function z. So as promised, this is a pretty crazy looking function. So this is the f of x y function. What I'm going to do now is over here, I have put in, you can see the difference between this line and that line is that on this line, I have set y equal to 1. So there was a y cubed, I put a 1 there. There was a y squared, I put a 1 there. There was a cosine y, put a cosine 1. So now I'm going to turn on that second function. And you can see it's a little hard to see because it's that curve, right? So notice if I go up there, you can see here, this is y equals 1, and the curve kind of goes down very quickly. And then it levels off a little bit, and then it just plummets. So we'll take another view. Of that. You can see the curve plummeting there as we get closer and closer, as x gets more and more negative. So I'm going to turn off now the surface. Actually, I'm going to make the surface not be so in our way. So I'm going to say, actually, let's turn off the surface first so we can go back to what we were seeing before. So notice that this is the graph of the curve f of x comma 1, right? That's exactly what's over here. Z equals f of x comma 1. So if I go to y equals 1, there it is, and I look at z as a function of x, I would kind of have to look this way. There we go. Then this is z as a function of x, so I get this nice little curve. And, you know, if you saw this, you would think, oh, it's a single variable curve. So I can just calculate the derivative. I'll get z prime of x. In doing so, you're calculating f sub x of x comma 1, because we're looking at the curve at y equals 1 on the function f of xy. Moreover, because we were interested in the example at 1 comma 1, if I go on this curve at x equals 1, let's see if I can get it more or less. Great. One more. There we go. If I go on this curve, at x equals 1, then here's x equals 1. If I go up to the function, I'm kind of here. If I drew the line that's tangent to this curve at x equals 1, then the slope of this line would be 5.5. That's the value we calculated in the example, and that's what this means. So if I turn back on the function, you can see that what it's telling me is that if I'm moving along that curve at x equals 1, there is a very, very steep gradient or slope Actually, that word gradient will come up later in the course. So that's just a quick visualization of what was happening in this example. Okay, we'll do one more example, and I'll mention some quick little things to wrap up. First thing I want to mention is, just like you did in single variable calculus, if you can differentiate once, you could probably differentiate a bunch of other times. What's different in multivariable calculus is that you can mix the directions you differentiate in. So these are called higher order partial derivatives. You could start with fx, and then you could differentiate with respect to x again. You could start with fx, but now you can differentiate with respect to y. So there's all sorts of interesting combinations that you could try, especially as you add other letters here. One thing to notice about notation, look here. So fxy means first you calculated the partial with respect to x, and then with respect to y. On the other hand, if I do df dx, it means you first calculated the partial with respect to x, and then if you calculate the partial with respect to y of that, you would get the second partial, dy dx. Very important, notice that these letters are in reverse order. And this is, the whole point of this equality here. So when you're using the notation of partial derivatives in subscript notation, you read from left to right. This was the first partial that was calculated, and then it was this one. When you're using the notation of partial derivatives, like the del notation, you read from right to left. Here, this was the first partial that was calculated, and then it was this one. So keep that in mind as we do these examples. So next and last example in this video, let's find f sub xy for this function here. And then let's also find this one, which again is not the same as this, because we would differentiate with respect to y first, and then with respect to x. Although there will be a surprise at the end of this, which will take us out of the video. So let's start with f of x being this function. Fx is 2x plus, I'm thinking of y as a constant, so just to differentiate x to get 1 times the constant, y. And then I'm thinking of x as a constant here, so derivative of y squared is 0. So that is my fx function. And then now going up here to calculate fxy, I'm going to calculate the derivative with respect to y of this. So thinking of x as a constant now, I only need to get a contribution from this term, which is 1. Great, so now I'm going to go back and do the same thing, but in a different order, because I'm going to calculate this one. So I'm going to say, okay, df or del f del y, thinking of x as a constant, that goes away. Derivative of a constant stays because it's being multiplied by y, whose derivative is 1. So I keep the x, and then derivative here, now y is the variable, so minus 2y. And then to calculate this, now I differentiate this with respect to x. So now x is the variable. Its derivative is 1. Y is the constant. Its derivative is 0. So I'm done. One thing you'll notice, we have gotten the same thing. So what we have obtained, if I write this in subscript notation, we differentiate it with respect to y first, and then with respect to x. So what we have obtained is that fxy equals fyx. This is referred to as the equality of mixed partials. Partials refers to partial derivatives, and mixed refers to the fact that we are mixing here x and y. Question, is this a fluke, right? Do we always get equality of mixed partials? Is it just for this example? There's actually a theorem that tells us this. So this is Claro's theorem, and it tells us, suppose that f is a function defined on some disk in R2, and AB is a point in this disk. If the mixed partials are both continuous, then the mixed partials are equal at that point. Long story short, this is one of the reasons we discussed continuity even ever so briefly in the previous lesson. As long as the functions that you have found, the mixed partials you found, are continuous on a certain domain that includes a certain point, then the mixed partials at that point are equal. That's effectively what was happening here. We saw in the previous lesson that multivariable polynomials are continuous everywhere. This is a multivariable polynomial, so its partials, no matter how mixed or not they are going to be other multivariable polynomials, and they're also going to be continuous everywhere. So long story short, for every multivariable polynomial function, the mixed partials are always equal everywhere. So that follows again as a corollary of this theorem. Okay, so we've done a lot in this video. It's be very hard to summarize it, but I'm just going to scroll up very quickly and mention a few things. I definitely encourage perhaps watching this video maybe twice, or at least 1 or 2 more times, because this is the foundational concepts that will underpin the rest of this unit and a lot of the rest of this course. The basic idea being that we took a 2-variable function and we played some trickery. We turned it into a single variable function by fixing one of the variables, by making them into a number. So think of f of 1 comma y or f of x comma 1. In doing so, that produced a single variable function. And then we realized, hey, single variable function, I can differentiate it like I would normally using my limit definition of the derivative. That led us to define the partial derivatives of the function as the usual limit definition of the derivative, except we were only changing one variable at a time and leaving the other one the same. And those are what we've now called partial derivatives. The actual value of a partial derivative, something like this down here, can still be interpreted as the slope of a tangent line. But it's a special tangent line. It's the tangent line, like over here, the line that is tangent to one of these curves obtained by setting either x equal to a number or y equal to a number. So go back to this picture to have that in mind, right? Remember that curve right there that we, this one, that we obtained by setting y equals to 1. So after that, that's all the intuition. The mechanics of calculating partial derivatives will take a while to get used to, but hopefully it'll be second nature after a few practice problems. If you're differentiating with respect to x, everything that has a y in it, think of it as a constant, and then use all the single variable calculus rules. The derivative of a constant times a function is the derivative of that function times that constant, for example. And the last thing that we covered in here that's important to know is mixed partials and just higher order partial derivatives. The change in notation, again, is important. If you're doing subscript notation, going from left to right is how you're differentiating. First in x and then in y in this notation. If you're doing del notation, it's the other way around. This means first calculate the derivative with respect to x and then with respect to y. And then this equality of mixed partials question came up, was answered by this theorem, and for the special case where f is a multivariable polynomial like this, mixed partial derivatives are always equal everywhere because, as we saw in the previous lesson, these functions are continuous everywhere. Great, so thanks for sticking around for this long, and I'll see you in the next module.